So the very first step you would do on a question like this, Ben, is just call this R just to make the algebra a little bit easier, and this one S.
Yeah, yeah.
Okay, because you're trying to prove that both of these satisfy the wave equation.
I did the one for X, and now I'm doing it for T.
Yeah, and so now what you have effectively is F is a function of R, and R is a function of X and T.
Right.
Or wait, F is a function of
R.
R and S, because you have an S here. Right. And R is a function of X and T, and S is a function of S and T.
Yeah.
And from here on, start doing partial derivatives. Yeah. Start figuring out the Laplacian first. So I'm going to do it here. So d squared u over d squared u is just d squared, and but u, by the way, is f, so d squared f, yeah, d squared u is d squared f over dx squared plus d squared f over dy squared plus d squared f over dz squared, and those two would be zeros because there's no y and z. So we're gonna start doing df over dx. So this is from the tree, df over dr times dr over dx plus, so we go over this branch, this is df over dr, dr over dx plus df ds, ds dt. So plus df dr ds times ds dt. Okay, so now df dr stays df dr because we don't know what f is. So this is df dr, and dr dx, well, r is x minus vt, we called it that, and s is x plus vt. So dr dx is just 1. So this is 1 plus df ds, we don't know, and ds dt, ds dt, oh wait, oops, we made a mistake here. Df ds dx ds dx, this is supposed to be dx dx. So ds over dx is also 1. So that means df over dx is just equal to df over dr plus df over ds, which means this is the same thing because partial derivatives are distributive with addition. We could say this is d over dr plus d over ds operating on function f, which means since these two are the same, we can now say d over dx is just equal d over dr plus d over ds. I'll come back to that in a minute. Okay, and now we go ahead and do the second derivative because the Laplacian needs the second derivative. So so now I'm gonna start doing the second derivative. So d squared f over dx squared, this is the same thing as d over dx of df over dx, and this is the same thing as d over dx of d over dx of f, which is the same thing as d over dr plus d over ds of f. or I could just, yeah. So this becomes, if I distribute this, um, oh wait, d over d, oh yeah. So now, and then this d over dx, the first d over dx is d over dr plus d over ds times d over dr plus d over ds of f, because this guy is just this guy, d over ds. So now if we distribute the second partial derivatives, we get d squared over dr squared plus 2 uh, 2 d squared over dr ds plus d squared over ds squared, and all this is operating on function f. Alrighty. And so what I found here is basically uh, d squared u, which is the Laplacian. So let's circle that. And now, so this is the left-hand side. And now we go and we prove the right-hand side is the same exact thing as the left-hand side. You can compare your answer if you got the Laplacian. The Laplacian should be this. Right? You see it?
Well, I did it for R first.
Oh, you done them separately? It's probably easier if you merge them together. Oh yeah, definitely using partial derivatives, because
I mean, like,
if you look at the tree, f is a function of r and s.
Yeah.
So you could just work them together at the same time.
yeah. Although, but I actually plugged something in for R. And,
R is x minus vt.
yeah. And so when I got to the derivative part, I plugged in for the second derivative part. I plugged in the drdx.
Now you have to be careful with the second derivative part, because the second derivative, when you get to d, you see, when you get to the second derivative, you actually have d over dx of d over dx, but d over dx is d over dr plus d over ds. So then you're going to end up with cross terms.
Well, but I didn't get that because I did it one at a time.
Okay, continue. Let's see if you get the left-hand side.
Well, for R, this is what I have. I have df is that,
But you didn't get them to be the same. They're not the same. Where's the Laplacian?
What was the Laplacian?
D squared u, this gradient squared of u.
That's the change d squared f dx squared. That's because it's only in x. X is the only spatial component. So then that would qualify as the Laplacian.
How do you get from here to here?
Oh, I plugged in that, so d squared f. We don't know. This is arbitrary because it's f, but the rdx is 1, and d squared rdx is 0. So this times 1 would be what this whole thing comes out to.
Yeah, that's right.
And then for the t part, same procedure, except we have it's v instead of, or negative v instead of 1.
squared f dr over dt. Dr over dt. Wait, what's d squared r over dt?
Well, that's zero because it's
0. So this becomes right,
might
but
just be
then, but wait, your answer is not the right answer because here you have 1 over v squared.
yeah, I know. That's I'm kind of puzzled about that.
All right. Um, I don't know. Let me review your algebra. Hmm.
Maybe if I plug in that, it's x dx dt. I plug dx over dt for v maybe. I guess I will try to do it.
Okay, I'll continue it here my way. So now I'm gonna go find uh, d squared u over dt squared. So let's start with du over dt. So du over dt, which is the same thing as df over dt. So now I'm going to go back to the tree. So df over dt would be df over dr times dr over dt. So df over dr times dr over dt. Okay, df over dr times dr over dt plus, so back to the tree. So this is dr over dt here, plus df over ds over dt. df over ds over dt. And so df dr is just df dr dt. Well, r is x minus vt, so dr dt will be minus v, plus df ds is df ds. We don't know what f is. And ds dt is also plus v. So this guy here is df over dt. Okay, so now we're going to do d squared f over dt squared. So this is going to be d over dt of df over dt, and df over dt is just minus v df over dr plus v df over ds. Okay, and so we're going to get um, um, we're going to get minus, now df over dr and df over ds. df over dr and df over ds. Okay, so what's df over dr? Df over dr arbitrary. So this becomes let's pull out the v. So v into d over ds minus d over dr of f d over dt. Yeah. So I could put the d over dt here. Yeah. And now df over dt using the tree is df over dr over dt. Oh, it's just the same thing. It's this, another v times uh, times so there's another v times d over d s minus d over dr. Okay, so then this becomes v squared, because this times this, times, and there's an f here, function f, they're all operating on f, so this is just d squared s d squared over ds squared minus 2 d, so I'm just foiling the partial derivatives, d over dr, d over ds, so d squared over dr ds plus d squared over dr squared, all operating on f. Alrighty. Um, and now we are trying to prove that if we multiply this by 1 over v squared, um, yeah, so if I do this, minus, minus 2. Okay, wait, there's something wrong with a minus sign here. dr over dt is minus v1 is plus v. dr over dt is minus v. Yeah, so here the only way that this will work out. Okay, good. So we do have them equal on a condition. Now, let me multiply this first by v squared, right? Because one of them is 1 over v squared. So if I do 1 over v squared of d squared uh, u over d squared u over dt squared, the v squared will cancel out and I will get the rest on f. dr ds plus d squared over dr squared. Okay, and I got for the Laplacian the same thing, except here I have 2d squared over dr ds. So we are off by this sign. Okay, so for these two to be equal, this guy needs to go away, which means the only way that these two are equal is if this term here, uh, if this term here was 0. In other words, if these two terms, if one of these two terms is 0, so if d squared f over dr ds equals 0, meaning what? Meaning d over dr of df over ds equals 0, meaning df over ds is independent of r, right? Meaning df over ds is independent of r, then only in that case d squared u will equal. So if these twos are zeros, then they're just going to drop out and we're going to get Laplacian of u equals 1 over v squared d squared u over dt squared. Okay, man. So that means for this to work, df over ds has to be a function of s alone. At most, a function of s alone. Um, so that means f has to equal some function of s plus a constant c if we integrate.
It could also be R alone, right?
It could be yeah, any function of r alone. Correct, either way, for this to work. So yeah, so our g could equal g of r or big G could equal g of r plus some constant c. So then a solution of our above equation could be f equals f of x minus vt plus another function of x plus vt, where these are arbitrary functions. Or we can just change the name of that and call it g. Okay, this is the Allenbert's solution of the wave equation.